I want to go through example 5.4. No marker there. I think I bring all my markers home. Okay. Hanya tak boleh. Okay, so tandakannya like G ada kat ada space. Okay, G is equal to special linear group. Can you see this? Anna cannot answer, you can easily see. Is it okay? Okay? Okay. Okay. I have to move my class to my office because there's construction at home. So noisy. Okay. So G is special linear group, 2 by 2 matrix. So by saying this means if A in G, the determinant is 1, yeah? GL is determinant 0, SL is determinant 1, okay? And then M, 2 by 2 real matrix with non-zero determinant. M is actually in GL, okay? M, any 2 by 2 real matrix with non-zero determinant. Now we define phi of A based on this M to be M inverse AN. Okay, for all A in G. Now we want to show that this is an isomorphism. Okay. Okay, first of all, you have to show that this mapping is well defined. Well defined meaning, if you map A, do you get something in A? Okay, even before you check one-to-one onto homomorphism, is it well defined? So if you have phi, okay, from G to G, the image of A, is it back in G? So how are you going to check? You need to find the determinant, because if you map one element in G, which is A, the determinant is 1. What about the image? Is the image also has determinant 1? How do you check that? You cannot write in terms of this. Yes, it's 2 by 2 matrix. And you saying this, AD minus BC is 1. But you don't need to show in AD, ABCD. You can show it just by determinant. So how do we show it's well defined? Check whether phi of A is also in G. How do you check? Phi of A is M inverse AN. My voice, is it clear? Okay, make sure you can hear me and you can see me clearly. Yeah. Okay, so Okay. So you want to check the determinant, right? This is because A is in G. Now, determinant of A inverse AM, determinant of a product is product of the determinant. You have to remember this from linear algebra. Okay? What is the determinant of an inverse? Of a matrix. What is the determinant of the inverse?
1 over.
1 over.
Yeah.
Okay? So this is actually, if you want to put like this becomes now a number. Yeah? Which is actually, from linear algebra, is this. Okay? And what do you get? Now they're all numbers. Determinant, they're all numbers. So, you get, again, determinant of this, which is 1. So, this is an element of C. Okay? So, this is, although it's not under isomorphism, but it has to be well defined. Okay. Next, we show it is 1-to-1. Okay. Check whether this is 1-to-1. So let phi A is phi B, show A is B. Okay. Phi A is M inverse AM. Phi B is M inverse BM. How do you get rid of the M? Now, it's given that M is a 2x2 real matrix with non-zero determinant. That is why we have this. So when the determinant is not 0, this means M inverse exists. Right? So when M inverse exists, so we multiply here by M, multiply here by N inverse. They are all elements of group, so they are all associative. Instead of this, you can move this, right? I didn't show one by one. So this is identity, A identity, identity, B identity, so A is B. So it's 1-to-1. Okay, the next one is to show it is onto. Okay. Okay, now to show it is onto, meaning phi is from G to G, phi of A is M inverse AM. So to show this is onto, find A in G. Okay, no. We do this. Given B in G, given B in here, find A in G, find A in here, that is map to, onto means, given anything in here, find A that is mapped to that. Okay, that is onto. Given anything in here, there has to be something mapped to that. Okay. Right? Okay, so, all right, so I erase this. Okay, so, okay. I have two of myself suddenly. Okay, so such that phi of A is B. Okay, so given B in the other side, find A from this side that is mapped to that B. Meaning you have to find A in terms of B. It's actually quite easy. You have to find A in terms of B. Okay, so what is phi of A? M inverse AM. Now, how do you write A in terms of B? Again, by using the fact that M has an inverse, so you multiply. Don't divide or anything. This is a matrix, yeah? Don't divide. So you multiply here by M, and you multiply here by M inverse. So you have to multiply both sides, the same thing. Then this cancel, you get A is M, B, M inverse. And this is again in G with the same reason, the determinant is 1. Okay, give me any B, you just multiply like this, you will get the A that is mapped to that. So it's on 2. So this is one way to show it's homomorphism. Not yet. We haven't shown it's homomorphism. Okay, last one. Another way to say preserve operation. Okay, actually it's more comfortable for me to stand up and teach rather than to sit with the small, so small. Okay. So what do we have to show? We have to show phi AB, is it equal to phi A, phi B? The best way in proving is you start from the left-hand side, and then you go right, and you show is equal to the right-hand side. Okay, instead of taking left-hand side and then stop, taking right-hand side and stop at the same place. Actually, you can just go, right? What I'm saying is, if you take the left-hand side, you put equal, equal, maybe it's equal to 1, right? And then you try right-hand side equal, 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 and then you get also 1. Why not you just do? Right? Then you get the right-hand side. Because sometimes you get stuck. You don't know how to move on. Then you can start. Okay, now you take the left-hand side. What is the formula? M. What is it? M. Inverse, right? A, B, M. Right? Okay. Because phi A is M inverse AM. So phi AB is M inverse ABM. Now, you want to show at the end that this is equal to this. Right? And then how do you show it equal? This is what I said. Sometimes you get stuck and then you start from the end. This is like actually cheating, but do you see it? Right? Because you insert I in the middle. Right? Instead of this, you put, right? How do I know to insert this? Because I start from the other end. So this is the best way to show from here to here. Why do I insert this? Because I want it like this. Okay, so sometimes you have to start from the other side. Okay, so this is just I, right? Because I want to separate. Okay, Then you, so this is an isomorphism. I think one of the assignment has something similar that you have to show something with this one, something with isomorphism. Okay. Okay. I have gone through example 5.7, yeah? I want to go through the properties of isomorphism. I have said this, but I haven't gone through one by one. Okay, this is from section 5.5, some properties of isomorphism. Number one, the image, okay, if you have phi from G to H, yeah? The image of the identity in G is the identity in H. So you always map the identity to the identity. Okay. The second one says the image of the inverse of A is the inverse of the image. The image of the inverse is the inverse of the image. We are talking about A here. Since it's a group, it has an inverse. There is a mapping here, isomorphism. So A is phi A, and this also has the image. And since H is also a group, every element has the inverse. And it turns out that this is actually just this inverse. Okay, it's nothing else. It's the inverse of the other one. So the inverse, the image of the inverse is the inverse of the image. That is what it means. Okay. The third one, phi of A to the n is phi of A to the n. Okay. And let me show you how actually you want to prove. Okay. You can try proof number one. Let me prove number this. You know B is A inverse if and only if AB is E, right? That is the definition of the inverse. Now we want to show that this is this inverse. So I just multiply phi A times B by homomorphism when I put homo is homomorphism, yeah? It's not other homo. It's phi of E is equal to E from here. Okay, phi of E is E. What does it mean? When you multiply A with B is equal to E, so this is this inverse. Okay, to show something is an inverse. Okay, I repeat. To show something is this inverse is by multiplying AB or BA and show it is equal to the identity. We want to show that this B is this A inverse. So you multiply the B with the A, or B, A with the B. Okay, we multiply A with the B. By homomorphism, you can multiply the inside. And since A inverse is element of G, it's E, and by 1, it's E. Okay, since AB is E, B is A inverse. Since AB is E, B is A inverse. All right? Okay? Okay or not? Okay or not? Okay. Okay, now I want to show this. It's quite straightforward using homomorphism. Okay, phi of A to the n is phi of A n times. Right? N times. This is by homomorphism. And every 2 is associative, right? You have to do 2 by 2. But 2 and then 2 again and then 2 again until n times. So this is this to the n directly by homomorphism. Okay. Okay. Now number 4. Number 4 says AB equals BA if and only if phi A phi B is phi B phi A. It's very easy to show, right? Using homomorphism. Okay, let's try. Phi of AB is phi A phi B, but since AB is BA, phi of AB is also phi of BA, which is phi B phi A. So phi of AB from one side is phi A phi B. Phi of AB from the other side is phi B phi A. So we got phi A phi B is phi B phi A. What does it mean? It means if G is a billion, H is also a billion. Okay? If H is a billion, G is also a billion. So let me write this. This means what did I want to say? Oh, G a billion if and only if H a billion. Okay, so if G is a billion, then H is a billion. If H is a billion, then G is a billion. Since it is an if and only if, not also. If G is not a billion, H is not a billion. Okay, and the other way around. Okay, so if they want to be isomorphic, they have to have the same property. Okay. Okay. Number 5, again, G cyclic, H cyclic. Right, again for this one. Next one is the order of A is the same as the order of the image, meaning you have to map one element to the image of the same order. Okay, you cannot map of a different order. 7 says the inverse is also an isomorphism from H onto G. So if you have phi from G to H, you can have also the inverse mapping, also an isomorphism. And last one, as the properties of isomorphism, is that if K is a subgroup of G, okay, then phi of K, I call it, don't call it anything, just phi K is a subgroup of H. You map a subgroup to a subgroup of the other one. Okay. Number one, the properties I mentioned, that is the simplest one. Okay. The proof is there, 5.5. I just show you the proof of number 2, theorem 5.6. Okay. And that is a theorem 5.7. There is actually another property. I didn't list as property, but it's a property too. If G is isomorphic to H, they have to have the same order. I mentioned this in the very first time we did this, because you want to be one-to-one and on-to. Okay. Theorem 5.8 is very important. Any finite cyclic group of order n is isomorphic to Zn. Theorem says this. Let G be a cyclic group of order n. Then G is isomorphic to Zn. This is another way of saying any finite cyclic group of order n is isomorphic to Zn. How do you map? Okay, how do you map? G, say generated by G. Okay, what is the element? E, G to the 0, G, G squared, until this. Because it is a cyclic group of order n. What about Zn? Okay, Zn is generated by, maybe, generated, right? 0, 1, 2, until n minus 1. You can still see at the bottom, right? You can still see? Okay. Now you see, you map. Right? That is how you map. So if you want to show this, the proof is you have to show the mapping. So phi is from G to Zn. Phi of G to the I is I. You map G to the that to that number, right? So G to the I from here. And you have to show this is an isomorphism. Okay. First, this is in Zn. Okay. So I from 0 until n minus 1. Second one, you have to show it is 1-to-1. Phi of Gi equals phi of Gj implies I equal J. Okay. The onto given any I in Zn, Okay. Find X in G such that X is mapped to I. So let just X equals G to the I. Then onto. So that is how you show is an isomorphism. Okay. Okay. I mentioned also about the kernel, right? Kernel. All right. Let's see some more examples. Okay. Decide whether G and H are isomorphic or not. I just do like this. Easy. Z plus 2Z plus Z plus R plus let me change this to R. Okay. Three R plus SL 2R multiplication D4 dah juga of order 8 ya. Dah juga order 8 quaternion group of order 8. Okay. Oh, this one. S4 D12. When I put dot, it's just the composition, or the U8 and U10. Okay, I give you some time, maybe 5 to 10 minutes to think about this, to look at the properties, look at the characteristic of the group. Okay, if you want to show that they are isomorphic, you have to give the isomorphism. You have to give the mapping. Okay, so I give you 5 minutes. Think about this. Okay, everyone is done or not? I need volunteers, but only one for each question, yeah? Who wants to try the first one? You can raise your hand. Who wants to try? It's quite an easy. So you have to tell me yes or no.
Yes. Yeah, the first one is isomorphic.
Hassan, you have to be quiet today. Give the juniors to answer, especially the one master student,
Okay.
to get grade for this class.
Yes, doctor.
Lava, can you try and why?
Yes, doctor, because the function is one-to-one.
You have to give me the function first. What is your mapping?
Pn equals to 2n.
Okay, so first you take any n in Z, any integer, right? And the image 2n is in 2Z. Okay, so it's well defined, right? The first one is one-to-one because if you phi n equals phi m, so 2n equals 2m, divide by 2 is a number, so n is m. All right. The onto one, you take any y in 2z, so y is equal to 2k, right? K in z. So find x in z such that phi x is y, which is 2k. So let x equal k, right? Because k will be mapped to 2k, which is y. So this is showing that phi is onto, right? 1 will go to 2, 2 will go to 4, and so on. If I change this to z, you can change also, right? It's to itself. I can also change this to k, right? So z is always isomorphic to kz. This is infinite. It's not like this is more than this one or not. Okay, infinite, you cannot compare the order. Okay, Lava? One more, right? You have to show also preserve operation or homomorphism. Okay, so this is on to phi of m plus n plus, yeah, it's 2m plus n, which is 2m plus 2n, which is phi m plus phi m. Okay, Lava, is it okay?
Yes, phi is an isomorphism.
Okay, so phi is a homomorphism or preserve operation. Thus, phi is an isomorphism. And since it is an isomorphism, lastly, you will say Z is isomorphic to Z. Okay, or you can say Z is also isomorphic to KZ. Okay, can be any. Okay, clear? Okay. Okay. Now, who wants to try the second one? Except for Hassan or Shiham or Hannah.
Professor,
Yes.
because question number 2 is not perceiving the operation has become multiplication.
Which one?
Has become multiplication.
For this one? This one you mean? Number 2.
The operation plus and multiplication.
This. What's wrong with this?
If isomorphism must be perceiving the operation, was it necessary to perceiving the operation of
Yeah.
isomorphic?
Yes. Yes.
So the operation in the U is plus addition, so the H is multiplication, so not perceiving the
Not necessarily. You have to tell me the mapping. Before you said it does not preserve, you have to give me the mapping. What's your answer, yes or no? You have to give me the mapping. If it is no, you have to find properties that are different. Because if it is not true for one, it might be true for other mapping. Okay? If they are isomorphic, you have to give me the mapping. Can anyone here? Can anyone here give me a mapping?
No.
What about phi of x
Yes, power. Yes,
is it?
yes.
Who said yes? Where is the one who said yes? Oh, empty. I cannot see.
Okay.
Suppose, how do I know this? Because I need onto. I need, you know, how do you draw a function which is one-to-one and onto the xy axis? Okay, one-to-one and onto. Onto means it has to cover the codomain. It has to cover the codomain, which is R plus. So it has to cover this to the top. Okay, without this. This is not included. It has to cover all. Draw a function that cover all. One-to-one. One-to-one means we can use vertical line test. Meaning, when you draw a function, continuous, you draw one vertical line test, vertical line, it will intersect only at one place. That is one-to-one. Like this. This is a one-to-one. No, sorry. This is for function. Take it back. Horizontal line test. Vertical is for function, yeah? Vertical is for function, okay? So this is not one-to-one, right? Okay. So, okay, onto and vertical. So I'm thinking, if you have this, and you have to cover all, okay, domain is all. So you have to cover everything.
Doctor, Professor. 1-to-1, not vertical line test. Vertical,
No, no, no.
vertical.
Horizontal line test. Vertical is for function.
One domain, one x value with y value. No one x value to 2 to 3 y value.
No 2x value will go to 1. No
No
2x value will go to 1y. That is 1 to 1. So if I draw like this, okay, if I draw like this, y is e to the x, right? Anna, yeah? You remember this exponential function or not? Okay, so this is just one example, or any a to the x, right? Empty none just now, you said. So this is 1-to-1. It's onto, okay, onto, because it covers all on top. 1-to-1 because of this. But you also have to check preserving operation. Okay, if this satisfies all those three, so this is an isomorphism. So I can say these two are isomorphic. Okay, if this is not an isomorphism, you cannot say they are not isomorphic because there might be other mapping. Okay, understand so far? I haven't finished. All right, this is how I got this. Okay, but I haven't write down the proof. Okay. Claim this is an isomorphism. First, phi is 1-to-1. Phi x equal phi y implies 2 to the x equal 2 to the y, imply x ln 2 is y ln 2, imply x is y. We just divide by ln 2, natural log or LOG. Second, phi is onto. For all y in R plus, find x in R such that phi x is y. Is still clear, right? Okay. Okay, so you put in the formula. Okay. The formula you put in. I will erase this, 1-to-1. Okay. So phi x is y, imply 2 to the x is y, imply x ln 2 is ln y, imply x is ln y over ln 2. And since y is in R plus, okay, ln y over ln 2 is also in R. In R, x in R. And you don't have, since y is always in R plus, you can always find the natural log. You don't have the negative, right? So it can be negative if this is less than 1. If it's less than 1, it can be negative. So this is okay because y is always positive. So the natural log is okay. Okay, so it is onto. Now the third one is to show its reserve operation. Onto, yeah? Third one, Vx plus y plus, yeah, is it equal to Vx Vy? Okay, Tan, this is why I choose this question, because I want this to work. If I don't put this, this won't work, because this is 2 to the x plus y, right? 2 to the x times 2 to the y, Vx, Vy. So it preserves operation. So it's a homomorphism. So it's an isomorphism. Okay. So it's quite hard actually if you are not given a mapping to come up with your own mapping, because the answer is not unique. One can give e to the x, one can give 2 to the x, one can give 3 to the x, another one can give a to the x. So all of you can probably give me another kind of answer. What about like this? Can this be a function? It can, right? It's also one-to-one. It's also onto. Okay? So that's another one. What's the formula? If you remember your calculus. What's your formula? It's the reflection on the y-axis. It's to the negative, right? Yeah. To the negative x. Okay, so you can have many answers. So the answer is yes. Example, phi to the, if I use n, will be 2 to the n. Okay, number 3. Anybody can try or guess. If nobody wants to try, then I will call Hassan. Ahmad, you want to try?
Yes. Number 3, bro. Number 3 as a master, yes, 1-to-1 or on.
No, my question is yes or no. Are they
Yes, yes.
Are they isomorphic? Yes,
Yes.
or no?
Yes.
You say,
Yes.
okay. Tan, yes or no? Yeah, Tan? I don't know. Ain, what do you think?
I think yes.
You think yes? Okay. Hana? Don't know. Shiham?
Don't know.
Yes or no, Shiham?
I don't know.
You don't know too. Okay, I give you a hint. Check whether the group is abelian or not. You just have to look. You don't need to calculate anything, right? Imanina?
I think is isomorphism.
Is this abelian?
Yes,
A plus B is B plus A.
yes. Abelian.
Is this abelian matrix under multiplication?
Mm.
Huh?
Abelian.
Matrix.
Matrix.
For a matrix, this is true.
Yes.
So you have two matrices A and B. You multiply AB is equal to BA. If you have two matrices, is AB equal to BA?
Oh, no. Sorry, no.
So is it a billion?
No, not a billion.
No, not a billion. So the answer is
Not isomorphism.
not isomorphic. Okay? So in the case that they are not, actually it's much easier just to find a property that it does not satisfy. If you say they are isomorphic, you have to find the mapping. You will not find the mapping. Okay? How can you find the mapping 1 to 1, on to even? Even is not satisfy this. Okay? Is this clear? So by the property, yeah? By the property, it cannot be isomorphic. Okay, number 4. Vian, what do you think?
I think no,
Why not?
because the default with 0 is abelian. But
This is-
this is
This is-
not
This is not a billion.
abelian.
This?
Yes,
This is a billion.
abelian. Yes,
So if you have I times J,
J
This is
times
equal?
I. Yes,
I think in our class, the very beginning, you have the Kelly table for quaternion.
yes,
And we already said Ij is negative Ji. Right?
yes.
So this is not a billion.
Not abelian. Mm.
This is also not a billion.
Mm.
Okay?
So yes, no isomorphism.
Why is it not isomorphic? They are both not a billion.
Not abelian. Mm.
Any other answer? They are both not a billion.
Mm.
They are also both not cyclic.
Mm.
Okay? If you want to find an isomorphism, then you have to find the mapping.
Mm.
Okay? For, you remember the property? An element has to be mapped to the image of the same order. Meaning, if they're isomorphic, you have to have same number of elements, same order. Okay? So, if you remember D4, oh, that is small. Can see it? This one is order 1, right? This one is order 4, this one is order 2, this one is order 4, this one all order 2. What about the order of the elements in Q? This is order 1, order 2. These are all order 4. Okay? So your answer will be, okay, you can map the identity to the identity. Now this group has 2 elements of order 4. D4 has 2 elements of order 4, but Q has 6 elements of order 4. Okay, first what you have to do or write is, yes, they have the same number of elements, right? This is 8, this is also 8. Okay. Things that you don't have to write, but you have to know. Oh, I have a tangga over there if I want to climb. Next time I will climb that ladder. This one. D4 and Q are both
Not abelian.
not abelian, not cyclic.
Not isomorphic.
This is just checking, yeah? Silau, nampak tak? D4 and Q are both not abelian. They are both not cyclic. So in that case, they have the different same properties. So you cannot use that reason to show they are not isomorphic. Next one, they have the same order. So they are both not abelian. They are both not cyclic. They both have the same order. Next, you list the element order because this is finite. Then you see they don't have the same element order. D4 has 2 elements of order 4, but Q has 6 elements of order 4. Because property said you have to map element of the same order to the image of the same order. There is no way to map 1 to 1 and onto with the same order. They have different order. So this is the reason why they are not isomorphic. Okay? Clear? Okay? So meaning you have to know this because I've taught you this. You have to remember. Okay. So this is the reason why, and the answer will be no. Okay. Right? You can also use of order 2. Okay, because they also don't have the same number of elements of order 2. I use order 4, but you can also write this one has this of order 2, this one has this of order 2. Yeah? Okay, so this the answer is no. Since okay, next. Very easy. Very similar. What's the answer?
No,
No, why?
not abelian.
This is also not abelian. This is also not abelian.
Abelian group. Yes.
This is not cyclic. This is also not cyclic.
Not cyclic.
Okay, so what you have to do is go back and figure out how many elements of each order. Okay, how many elements of each order? S4 has elements of order 1, 2, 3, 4. It has 24 elements, but each element have order 1, 2, 3, or 4, right? Page. Page. Is it the same page? 53. Yeah, okay. Elements of S4, there are 24 of those, but they are all element of order 1, 2, 3, 4. Right? D12 also has order 24. But D12 has an element of order 6, right? You know, in Dn, you have half rotation, and half reflection. Okay, for reflection, they're all order 2. For rotation, you have to figure out the order, right? How do you get, the first one is you divide. So I reserve this. You remember I will erase this because we're done with this, yeah? Okay, B12. Last time when you do, D12 is order 24, yeah? Last time we do D4, right, of order 8. So I get R0 and then R90. How do I get this R90? I divide 360 by 4. I get that. What is 360 by 12? 360 by 12 is 30, right? So you will get 12 rotation. Rotation. Okay, and then reflection, I will just mu or rho is the mu is rotation, right? So rho reflection. So I just call this the reflection, 12 of them. Okay. So this is actually the element, right? And element order, so it divide the group order. So element order divide the group order. Like this one, it divide 24, but you don't have any other elements of order 6 or 12 of S4. But this one, see, this one is of order 12, right? 12 times 3 is 360, right? Okay, so just use this one is already not showing not isomorphic. This one has no element of order 12. This one has element of order 12. The one that I mentioned just now is this one of order 6. So there are many reasons why they cannot be isomorphic, because you don't have matching order of elements. Okay, so the thing is not that difficult, just you have to know the property of the group. If you don't know what the group is, the property, the element order, abelian or cyclic, how are you able to answer? Okay. Last one. It's clear, yeah? Okay, so you can figure out this is element of order 4, element of order 3, and so on. Okay, last one. Yes or no?
No,
Why not?
you ate cyclic group, not cyclic group, but you
Not
change
cyclic.
cyclic group,
This is
cyclic.
okay, and also because they are both abelian, Okay, you cannot say this is a billion, this is not. They are both a billion. You cannot say it's isomorphic because they are both a billion. Okay, so but one is cyclic, one is not. Or you can say there is an element of order 4 here, there is no element of order 4 here. Okay, that is another reason.
Yeah.
Okay, I think I'm done with this chapter. All right.